So calculations for acid-base titrations. First thing you always will need is a balanced chemical equation. Then you're going to figure out the moles of what species you can calculate it for. Then you're going to use the stoichiometry to get the mole ratio, to figure out the moles of the other solution. And then you can calculate the concentration. So here we have hydrochloric acid plus sodium hydroxide. So this will make sodium chloride, sodium chloride, that's an arrow, and water, and everything's in a 1-to-1 ratio. So we've got 25 milliliters. Always convert your milliliters to liters by using the conversion factor. So we've got 25 milliliters of acid, which is 0.025 liters. We know we've got 1.25 mole per liter base and 18.62 milliliters, which is 0.01862 liters. So you're going to calculate the moles of base, convert it using mole ratio, and then you have moles and liters. You can calculate concentration. So moles of NaOH, 1.25 mole per liter times 0.01862 liters. So this is 0.02325 moles of NaOH. Convert that to moles of HCl. And now we've got 0.023275 moles of HCl. Now, concentration is moles divided by volume, so 0.02325 moles divided by 0.02500 liters, and it is 0.931 mole per liter. So our hydrochloric acid that we had 25 milliliters of had a concentration of 0.931 moles per liter. Now sometimes you're given a partial neutralization question. You'll have an instance where you've added this much acid to this much base. What is the pH? How much is in excess? So in this case we've got sodium hydroxide and hydrochloric acid. Again, write a balanced chemical equation. Because we have the concentration and volume for each, we can figure out the moles for each. We know that it's going to be a 1-to-1 ratio because stoichiometrically, that's what we get from their balanced chemical equation. So then we can figure out the number of moles in excess divided by the volume total to find the concentration, and then we can find the pH. Sodium hydroxide plus hydrochloric acid will make sodium chloride and water. So again, convert milliliters to liters. So we have 1 mole per liter, base 0.015 liters. Let's make that 15.0 milliliters. Hydrochloric acid, 1.2 moles per liter, and 0.0200 liters. So, figure out the moles of base, figure out your moles of acid. So moles of NaOH, concentration times volume, 1 mole per liter times 0.015 liters, 0.015 moles of NaOH. And now moles of acid, 1.2 mole per liter times 0.02 liters. So that is 0.024 moles of, I was going to write NaOH, HCl. All right, so there's more moles of acid than there are of base. So we're going to have excess acid. So figure out how much excess. You subtract the quantity of base from the quantity of acid, because it's going to be a 1-to-1 ratio. 0.015 moles of sodium hydroxide, because it's a 1-to-1 ratio, we'll need 0.015 moles of HCl. So moles of excess is 0.024 minus 0.015, 0.009 moles in excess of HCl. Now we have to figure out the concentration. We had 15 milliliters. We added it to 20 milliliters, so our total volume is 35 milliliters. So to find concentration, it's the moles of your excess divided by the total volume. So it's excess divided by total. So we've got 0.009 divided by 0.035. Our concentration is 0.257 moles per liter. So we have 0.257 moles per liter of excess hydrochloric acid. So pH is equal to the negative log of H plus. So the negative log of 0.257 is 0.589. So this is 0.590. So this is extremely acidic, right? It's less than pH 1. So when you added a certain quantity of acid to a certain quantity of base, partial neutralization happened until either the acid or the base was used up, and then you had excess reagent. You find the concentration of that excess, and then use that to find your pH. Now, What happens if you have a weak acid, strong base, or a strong base, weak acid? So we have acetic acid titrated against sodium hydroxide. So we end up with sodium acetate and water. All right, so write a balanced chemical equation, calculate the moles of acid to figure out the moles of base that we used. Identify the ions present at the equivalence point, so that's where your conjugate acid-base partner is going to come in. Write the equation for any for any ion that hydrolyzes with water, so that's our equilibrium reaction. Calculate the concentration of the ion before equilibrium, so that has to do with how much of our ion is present at equilibrium. Set up a nice table, solve for H. Okay. We will go through this. Okay. So in this question, we're going to figure out moles of acid, moles of base, and then that'll allow us to figure out our concentration of our conjugate partner in our salt. So moles of acid is 20 milliliters times 30 moles per liter, but of course we convert 20 milliliters to liters. So we have 0.006 moles of acid, and they will use up 0.006 of base, moles of base. And that's exactly how much we had. So all of our acetic acid, all of our sodium hydroxide was used up. But this is how many moles of acetic acid we had. So this will also be our moles of acetate. So the ratio of acetic acid to acetate is 1:1. So this means that we have 0.006 moles of acetate. Now we added 20 milliliters to 20 milliliters, so now we have 40. So to figure out our concentration of our acetate ions, we take 0.006 and we divide it by the volume. So we have figured out how many moles of acid we had, our weak acid, so that we could figure out the moles of our conjugate base, and then we figured out what our concentration of our conjugate base was in our flask. This is all pre-work. This is all before we can start doing our real calculations. So now we know our conjugate base will form an equilibrium with water to produce acetic acid, hydroxide ions. Okay, so this is where we need to start from next. So we've got our chemical equilibrium expression or reaction, and we know initially we have 0.15 moles per liter of our acetate. So we're going to set up a nice table. Initially, no acetic acid, no hydroxide for the reaction of our conjugate base with water. They will go through a change, and at equilibrium we will have this quantity. Set up your K expression. Always write it out with your formulas first and then plug in your values. It just doesn't pay to make shortcuts. So then this is equal to x times x, which is x squared, over 0.15 minus x. So, acetate ion, we need a Kb. Well, we know the Ka value. So if we take 1.0 times 10 to the negative 14, divide by our Ka value, we will get our Kb value. So 5.5, 6 times 10 to the negative 10 is equal to x squared over 0.15 minus x. And because 0.15 over our Kb is so much greater than 1,000, we know that 0.15 minus x is approximately 0.15. So we've simplified our life. So x squared over 0.5 is equal to 5.56 times 10 to the negative 10. So multiply 5.56 times 10 to the negative 10 by 0.15 and then find the square root, and we will have our x. So x is equal to 9.13 times 10 to the negative 6 mole per liter. And this is equal to the hydroxide ion concentration. So if we find the negative log of that number, we have POH, and then when we have POH, we can subtract it from 14 to get pH. So I'm just going to move this up and shrink it so we have more room. So the negative log of 9.13 times 10 to the negative 6 is 5.039. 14 minus 5.039 is 8.961. So pH is approximately 8.96, which is slightly basic, which makes sense because acetate is a conjugate base of a weak acid. So this is how you do a calculation involving a titration of a weak acid with a strong base. All three of these types of calculations are typical problems.